All right, let's get started. Thank you for joining us today. My name is Chase Bean. I'm the host today. I'll be moderating your questions, which you're welcome to post via the webinar's chat section. I'll point them out to Chris along the way during his presentation. We'll have a few polls during the presentation, so please participate in those. They'll pop up on the screen when they're launched. There's also a one-sheet handout for this presentation, so we recommend you download that handout and maybe open on a separate screen so you can follow along. It's like a control schematic, so Chris is going to kind of point out the different sections that he's talking about as he goes. If anybody has any trouble or doesn't see that, please let me know so we can post it again. And then also PDH certificates are available upon completion of the webinar. So please email me at that address here to request a certificate and we'll get that back to you. My info will be shared again at the end of the presentation. So you can do it then too. Steam Management is a premier energy conservation contractor providing custom design build solutions when you need to retrofit hydronic, water, or HVAC building systems for best performance, high efficiency, and resiliency. Using proven technologies and best-in-class designs, we customize energy conservation solutions, making it easy to achieve energy savings and facility improvements. These are our turnkey solutions. We focus on efficiency improvements in steam systems and other utility systems. These solutions reduce system energy costs, conserve water, and reduce carbon footprint by an average of 10 to 30% for most clients. The opportunities shown here are common measures that we evaluate and implement for our clients, but we do look at other opportunities as well. And today, we're thrilled to have Chris Hardy from Cross Company as our guest speaker. So Chris is a seasoned principal engineer at Cross Company. He has 30 years of experience. He graduated from Georgia Tech in electrical engineering and specializes in process controls. And throughout his career, he's been instrumental in optimizing processes across various industries, notably in boilers, pharmaceuticals, and wastewater management. Chris excels in fine-tuning intricate processes and seamlessly integrating communication across multiple systems within units, making him a go-to expert for tackling complex challenges. We recently partnered with Chris and Cross Company on a control valve automation and replacement project at a veneer mill in Louisiana, where we've replaced 14 steam control valves with electric valves and added control systems that indicated steam flow at each valve using valve position and differential pressure measured at the valves. The project also included programming upgrades that significantly improved the plant's steam system reliability and functionality. You can download the case study for that project, which is also posted in the chat, and we encourage you to read that after the presentation. Cross Company is Chris's company and a trusted partner of ours, and Cross Company is a leading industrial solutions provider specializing in engineering, automation, and control systems for improved efficiency and productivity across various industries. Cross Company was founded in 1954. It's employee-owned since 1979. 700 plus associates, all focused on improving customers' processes and products, and 30 locations across the United States. Now I'm going to hand the screen over to Chris, and while we are switching screens, I'm going to launch the first poll. So I encourage you to participate in that. And Chris, you can take it away.
All right, thanks for the intro, Chase. And good morning, everybody. All right, I'm going to share this. All right, so this morning we're going to talk about biomass stokers. And the idea with the biomass stoker is you are putting solid chunks of fuel in a furnace and boiling water. And so what we hope to take away from this is to learn about solid fuel combustion, what a stoker does. We're going to talk about the traditional stoker controls for coal, which is how traditionally stokers have been used mostly for coal, and some challenges where when you try to apply those controls for biomass, what needs to be changed to optimize for biomass. how to balance air, how to trim O2, and then we'll wrap up with some just general PID loop tuning techniques. So the goal again is to put solid fuel and air together, light them on fire, and boil water. So a little bit of history. The word stoker initially referred to a guy who threw fuel into a fire, usually coal. You'll also note that some of us are into smoking meat. And your typical smoker is I've shown a picture of the one that's on my front porch right now. This is a pellet auger, and there's a little fan down there, and the auger is a little screw that turns and delivers wood pellets into a little cup that burns, and there's a fan that blows air through it. And that's basically a small version of the large boilers I work on professionally. So many of you have actually used biomass stokers. Notice that stokers are chunks of solid fuel. So if your boiler is burning a fluid, meaning a liquid or gas, or it's burning pulverized powder, that's not really a stoker. That's a different delivery method, and that's not really what I'm covering here, although probably half the or maybe 2/3 of the presentation would also apply for that kind of a boiler. Okay, one important thing to understand about combustion of solid fuel, and really combustion of anything, but it's especially important with solid fuel, is that it's really a multiple step process, and we can broadly separate these into two sections. The first one is called pyrolysis or gasification, and in this step, the heat and some oxygen begin to combust the solid fuel, and what it does is it breaks it down and partially oxidizes it. The carbon goes to carbon monoxide, and the hydrogens and the hydrocarbons break off and become hydrogen gas. And so you can see, just looking at the compound chemical structures, that there's a little bit of oxygen being added here, but not very much. It's certainly not complete. And this does release some heat. That resulting mixture of carbon monoxide and hydrogen, and of course there's some other trace gases in there depending on what you're burning, but those are the primary constituents. Those are called synthesis gas or town gas. And then what happens is those, when they're heated and rise away from the wood or biomass, then fully oxidize if there's enough oxygen to fully oxidize the carbon to carbon dioxide and oxidize the hydrogen into water. And that also obviously produces heat. The picture of the match on the right, you can see that the flame is not visibly touching the match, it's off the match. And that's because the pyrolysis step, where you're gasifying the wood, you're not really seeing the flame there. And the flame is actually, what you're seeing is the synthesis gas burning. So that's the carbon monoxide and hydrogen burning, is what that yellow flame is. Any questions so far?
I don't see any in the chat yet, other than I guess the case study is not there yet. Actually, if you can put that in the chat, so people want to download it.
Okay. All right, so what I want to do is I'm going to show this versions of this slide multiple times, and what I want to do is kind of show the control scheme in an overview, and what I'll do is go through and define all these terms, and then we'll review it again when we're done with that section. And so in this process, you basically have 5 things that are important to measure and 3 things that we're going to actually control. So the 5 eyes on the top, those are actual measurements. So you have steam flow, furnace oxygen, and that oxygen is that's like 21% oxygen is normal air. And then, we'll run it down to something like 4 to 7%. You've got overfire air flow measurement, undergrate air flow measurement, and drum steam pressure or header steam pressure, depending on the setup. So that's what we're measuring. And then we have various controls, including PID loops, curves, and some biases. And then we have on our control elements at the bottom, we will be moving dampers, possibly changing speeds of fans, and certainly changing the speed of the augers, the screw augers that feed the solid fuel into the stokers. So that's where we're going, and so let's define our terms. Okay, probably the most important thing about what we're doing here and the major difference in what we're going to do for coal versus biomass is the air and the air balance. And so for a stoker in general, what you're doing is you're dumping solid fuel onto a grate, and that grate has a lot of holes in it. It's either round holes, or it's expanded metal or something like that, where it's going to hold the solid fuel on top of it, but allow air to come up from underneath. And so then you blow air into plenum under the grate. So that would be undergrate air. And then you also blow air into the space above the grate, into the furnace itself, and that would be over fire air. And so the solid fuel sits on the grate and burns. And what we're trying to do is supply enough air under the grate to complete pyrolysis and start the combustion of the synthesis gas, but to spread it out so that we're doing most of the combustion of the synthesis gas well above the grate. So we want to spread that fireball out, and you can limit NOx production and also make your kind of lower the peak temperature in the furnace while still having a great deal of heat transfer into the water and the tubes around the furnace if you spread that fireball out. And that's why we want several levels of overfire air to gradually complete combustion of the gases. Okay, let's talk about some differences between coal and biomass. Now, in general, for coal, both of the undergrate and overfire air go according to your boiler master. Actually, I'm going to jump back a couple of slides here. So the way a boiler generally works is you measure your steam pressure, and again, this could be drum or header, and then you have a PID loop that looks at the steam pressure, and if you say, hey, I want 2000 psi in the header, then if it's low, it's going to add more fuel, and if it's high, it's going to take off fuel. And then that goes to a boiler master, which there may be one or more boilers with boiler masters. In this case, we're just going to treat it as though there's only one boiler for simplicity. But if the boiler master sets both the fuel rate and the air rate, and for a coal-fired boiler, those go together, and that's the traditional way to do stoker control, is to have the overfire and undergrate together. Now, the difference is coal is typically a very consistent fuel. Even if it's sitting out in a yard in the rain, the wetness of the coal doesn't really vary that much because it doesn't really absorb all that much water relative to wood and other biomass. And when you dump the coal on the grate, it's typically a relatively consistent size, relatively consistent moisture, and usually when you have these large coal-fired power plants, they typically contract with a particular mine, and so they're getting coal that's consistent in quality. Whether there's a lot of different kinds of coal, lignite and anthracite and all that, various grades, but typically you're coming from a particular mine, and so you're consistent. And so the furnace just burns at a constant rate when you're doing coal. Now, biomass, by contrast, there's several differences. One is that the quality, the heat content, the moisture content, the size of the chunks of fuel is highly variable relative to coal. And also because there's so much moisture, what tends to happen is you end up dumping some fuel on the grate, and it takes a minute for it to dry out and really catch fire. And then once it does catch fire, it sort of takes off. And so the result is a cyclical burning in that furnace. And so it'll, you know, several minutes, you might have a couple of minutes where you're really slumping and not burning real well, and the steam pressure is maybe slumping a little bit. And then finally it takes off and the steam pressure will take off. And those cycles are, you can't eliminate them, but what we can do is manage them. And that's really the core of what this presentation is about. So as you can see in the slide, what happens is that once it takes off, the steam pressure starts to rise, the boiler master will back off, less fuel, less air, and then the if you do this traditional coal control scheme, you get more both the undergrate and overfire air back down, and when really you actually need more overfire air even as it's going down. And so this causes problems with your O2 control. And then once it catches going the other way, you really need more undergrate and less overfire, and the control system is turning down the overfire when you need more and raising it when you need less. And that's because they're both tied to the boiler master.
Hey,
now,
Chris, I got a, when you go back to that slide, I got a poll for it. So
about this one, or?
No, just the one on the, yeah. So
yep. All right.
Here we go. That's launch. So how do you handle variations in fuel quality and composition within your stoker combustion control strategy? You know, if you're not actually managing this, then just vote for what you think would be the most important. And that's it. Yeah, people can continue filling that out. You can go ahead, Chris. Thanks.
All right. Okay, so the alternative I'm proposing here is mostly similar to the coal. The main difference is you're going to break off the overfire air, and you're going to have it run based on steam flow, measured steam flow, and run it based on that. And so actually, let me look at the whole slide. So the idea here is you've got your undergrate is still coming from the boiler master. Now note that both of these flows come off of curves. So the boiler master has a linear relationship. This K means just multiply, and has a linear relationship to fuel. So if your boiler master goes from 10% to 20%, then your screws that deliver the fuel to the grate are going to go twice as fast because you have twice as much boiler master. However, the air is going to be on a piecewise curve, and those piecewise curves are so that your air is nonlinear, and typically you need a little more air proportionally at lower loads, and I mean, the air goes up, but it doesn't go up proportionally for higher loads. So you may have, if you double the boiler master, you may double the fuel flow, but you may only go up, say, 80% on your air on the undergrate. So what I'm proposing is, so for those curves, have the source of the curve for the overfire, instead of it being from the boiler master, is you have it from the steam flow. And so what that'll do is naturally have the air, undergrate air and the overfire air will swing opposite each other. And when your steam pressure is slumping, there's fuel on the grate, but it's wet and drying out, you need more undergrade air to help it dry out. One thing I should mention, actually, let me come back to here. These fans, this is a very simplified system of the fans in a furnace. By the way, I didn't mention this induced draft fan. That's just pulling the gases out of the furnace so that you can run a slightly negative draft pressure. Typically, though, what happens is you've got this very hot gas coming out of the furnace on its way to the ID fan, and you run it through heat exchangers. And so what happens is the air coming from the undergrate and overfire air fans runs past the air going out through heat exchangers and air heaters, so that it is very hot going into the furnace even before it's any of the oxygen is consumed. And so that hot air is also quite dry as far as relative humidity, and it will help dry out the fuel. So anyway, when the fuel is on the grate drying out, the undergrate, you need more undergrate air to help dry it out and get that pyrolysis going, but there's not as much synthesis gas rising, so you don't need as much overfire. So your undergrate's high, overfire is low. Once the fuel on the grate takes off, you need less undergrate, more overfire. And so they're swinging in the opposite direction. And that overfire is rising because the steam flow as a percent of your rating has increased. And then we trim that by O2, meaning we're actually monitoring the oxygen as it leaves the flue gas as it leaves the furnace. And we're going to adjust only the overfire air based on that O2 trim. We're not going to adjust the undergrate air. And I'll get to the details on that a little bit later. So they swing against each other, which is normal and fine. And then once the fuel takes off, they swing the opposite direction, and that's fine and expected. And the end goal is to obviously have a steady, as steady as possible of steam pressure, and that we fully combust all of the gases without adding a whole lot of extra air. One thing that, because you're having highly variable fuel quality, the operator has to have the authority to make an adjustment, a manual adjustment between the overfire to undergrate balance. And so what we do is we have a bias that is adjustable by the operator within a certain amount of percent. So you might have like a -20 to +20% bias. And what that does is allow them to shift that much air between overfire and undergrate. And so if the fuel is lighter than normal, smaller than normal, drier than normal, you're going to need less undergrate to pyrolyze that, to gasify that, and you're going to need more overfire to complete the combustion. And so they would shift the bias toward overfire air. By contrast, if you have heavier than normal, larger, or wetter fuel, you're going to need more undergrate air to get that dried out and gasified, and then less overfire on top to complete the combustion. And they should have the authority to make some amount of shift. So that's what's going on here. Okay, let's talk about this K again. I mentioned before, this is a linear relationship from the boiler master to the biofuel master. The biofuel master just tells how fast to turn the screw augers to deliver the chunks of fuel. However, what we need to do is actually have this K automatically adjust. And the reason is because we need a percent, like a 0 to 100% signal in the boiler master that goes to the undergrate air. And we need a 0 to 100% signal on steam flow that ultimately is the major determinant of overfire. And those guys need to line up. So if you have 50% boiler master, you really need your steam flow on a long-term average, say on like a 20 to 30 minute average. You need your steam flow to be 50% if your boiler master is 50%. And the thing that makes that happen is this K being correctly set. And it should automatically adjust. I have a formula that'll be in the notes, but we don't need to cover the math here. But the idea is you want to slowly, like if your boiler master is say 60% and your steam flow is only 50%, then that means you're not delivering enough fuel and you need this K to rise. And so you need to have the new K that matches the 50 to 50. And then you run that through a very long time filter, perhaps a 20-minute filter, and slowly adjust it. That filter needs to be several times longer than your cycle time. Your cycle time is typically going to be something like 5 minutes. And so that filter needs to be 10 to 20 minutes. So that's, yeah, you're dividing by the steam flow, run it through a long-term filter. Any questions?
Not seeing any in the chat, Chris.
Okay. All right. So continuing on, let's talk about the O2 trim. And so what we're doing here is we're measuring the oxygen as it leaves the furnace. And again, that is a signal that where it's the amount of oxygen as a percent of the gas. And so for the air we breathe, that's about 21%. And then we're going to burn and consume a lot of that oxygen to do the combustion, and it will run down. We don't want to let it ever go to zero, because that would mean that we've got synthesis gas back up in the ducts. And that is, it's an environmental pollutant to have that, but more importantly, those gases, when mixed in the correct concentration with air, are explosive, and we don't want to have explosions back out of the furnace. So we definitely don't want to go to zero. We want to have a little bit of oxygen left over to make sure that the synthesis gases are fully combusted. So one issue with a grate is usually a grate always has to have some method of moving the burned up material, the ashes that remain from that, down to the bottom ash collector. And so what happens is some of these grates have shaker motors on them, and they'll run maybe 2 seconds out of every minute, and they'll shake the grate, and the grate will be slightly tilted to run the ashes down. Other ones have walking or sliding grates where they kind of move back and forth against each other to shift it down. In either case, you've got this cycle, and particularly with a shaker, what will happen is when it shakes, it actually causes like the flame to jump up a little bit and consume more oxygen. So your oxygen will dip in the seconds following the shake. But this is predictable, and you know your shake. Typically, your controller that's doing the combustion control also has timers that initiate the shaking. And so what you want to do is run your O2 signal through a moving average. I think I see a question about, is furnace O2 smoothing necessary in fixed grate application? You do need to smooth the O2, but the moving average, I would say the way you calculate the time is not as important, but you definitely need to smooth it out, because that's a very noisy signal. For the periodic shake, you want to have a moving average that's on the period of the shaking. And what that does, this is different than a filter. This is actually an average, so that the samples that are more than a minute old just fall off and are no longer considered. If it's a fixed grate, or a grate that is moving that doesn't really have a period, then I would do something like a 30 to 60 second moving average anyway. And it really doesn't have to do with the technology of the measurement. It's actually it is a real the measurement, the noisiness of the signal is a real thing. It's not an artifact of the measurement method, because you're actually, the shaking causes more oxygen to be consumed in the seconds following the shake.
So in the fixed grate scenario, you don't have to tie anything to that particular action, right? That's with the
Right.
shaking. Like
You
in
would
the
just
other
have,
case, you have to kind of correlate it to when it's going to shake, right?
yes. Well, it's not really when the shaking happens, because what would happen is you would have, let's say you're going to shake, let's say the operator says, I want to shake once per minute. You would just have this cycle time that averages all of the samples for the last minute. And it doesn't really matter where in the cycle it is, because you're always averaging one complete cycle.
Okay. So your average
And then,
time is accounting for like having that shake within that time period, so that you're
right.
not too tight.
Yeah. And then what happens
Okay.
is if there is like an adjustable shake period, I'll actually take the period that is entered for the shaker and run that into a calculation that controls the sample rate. And so I'll have, let's say I have 60 samples. Well, if you have 60 seconds on your cycle, you're going to take one sample per second. But if they say, oh no, I want the shaker to shake every 40 seconds, well, now you're going to do every 660 milliseconds instead of once per second, so that
Okay.
samples. You collect samples for exactly one period. And so that way you completely eliminate the periodic upset from the signal that is going to the PID loop for the O2 trim. Now you want to report the actual O2 on the screen so they can see it moving around. But this is the O2 that's going to be used for the PID loop. It's really what we're talking about here.
Okay.
Then, back to that other question, if it's a fixed rate and there is no period, then, just set it to a minute and it's a constant. There's no logic to change that. So.
Okay. And if anybody didn't see the question, the second one was, is the noise less pronounced with a particular technology of O2 analyzer? So Chris's response is, it's not, because it's an action, it's a real reading, right? It's not like a function of technology. It's just like actually reading those variations.
Yeah. Now I will say, most advanced instruments, especially now, have smoothing filters inside them. So like you could go to the instrument and set the smoothing filter to 20 seconds or whatever, and then you would have less noise just because of that. But you're kind of imposing that filter on the raw signal, and it's just really a question of where you're doing that, not so much that the raw signal is any different.
Okay.
Okay. So the PID loop for the furnace, and again, this is what I'm looking at here is this loop right here. We just talked about having that average that happens between the measurement and the PID loop PV. We also need to talk about the set point. So the set point is going to come from the steam flow as a percent. So this is percent load. And you're going to run it through this curve. And this curve is typically going to be like when you're at low loads, perhaps 20% load. You might be shooting for like 8% O2 coming out the furnace. And then as your load increases, you're going to run that down to perhaps as low as 3 or 4% at 100% load. It's 3 or 4% oxygen at 100% load on steam. You also do typically want to give the operator the authority to adjust the set point coming out of the curve by a little bit. They might need to take maybe as much as 0.5% out or add as much as they want. And that'll be the set point for the O2 trim. I typically do not ever allow, this is always it's either in cascade or it's in manual and centered. I never allow just automatic, because what would happen is they could set it to 3% O2, and then if you dropped your load all the way down to 20%, that would not be enough O2 for that situation. You don't want to allow that. Anyway, and then what happens is the result of that O2 trim adjusts the resulting effective load going into your overfire air demand.
Chris, at lower loads, you have to have a lot higher O2. Is that okay? Is that just to make sure that you're combusting all of the fuel, or?
Yes.
Okay.
Yeah. So there's a couple of factors here. The primary factor is, you definitely want to have complete combustion, and basically the higher the load, the higher your airflow, the better mixing you have. And what you're doing is you're making sure that your synthesis gas is fully mixed and combusted with the oxygen by the time it leaves the furnace. And when you have lower loads, there's less mixing. And so there's more opportunity for there to be pockets of synthesis gas that don't mix with oxygen. And so having more excess oxygen is an effective way to make sure that does not happen. It does. The oxygen reaches the synthesis gas while it's still hot enough to burn before it leaves the furnace.
Okay. So it's about mixing as well as just having enough oxygen, because theoretically, like, the combustion only needs a certain amount of oxygen, but at those lower loads, you need the extra air for the mixing.
Yeah, it's insurance for complete combustion, really.
I got you.
And yeah, so in theory, you could do stoichiometric, which means exactly the right amount of oxygen for the amount of fuel that you have, and then you could in theory do that, but yeah, that assumes perfect mixing, which is this is the real world. There is not perfect mixing. So that's the biggest factor, is making sure you have complete combustion, and so minimal CO going up the stack, and you're going to need a stack gas analyzer to verify that you're hitting your targets. Typically, that O2 curve that we just talked about, this function right here, is typically comes as a result of a stack gas analyzer, and you run the boiler at each load and make sure that your stack gases are looking good. This also has it's very relevant for your NOx. If you get too low on oxygen, you can start, basically what happens is you actually oxidize the nitrogen that makes up 78% of our air. If you get spots in the furnace that are too hot, and this is one reason we want to spread out that fireball, is to decrease the peak temperature at anywhere in the furnace, because what happens is when you have hot spots with really high peak temperatures, that's where your nitrogen starts getting oxidized into NO2 and NO3. So the NOx, the X is 2 or 3. And that is, of course, an acid gas, and that's a pollutant that we want to avoid. Scrubbers are very effective at taking out acid gases like hydrogen chloride and hydrochloric acid and sulfuric acid. They're not really so effective at taking out nitrogen oxides. You really need like a selective catalytic or non-catalytic, where you're spraying in ammonia to react that. And if you can either avoid having those SCRs or SNCRs entirely, or use less ammonia by having proper combustion in your furnace in the first place. So, questions?
I don't see any in the chat. I was just thinking I'd point out, people that are dealing with mostly gas boilers. I mean, you never want unburned combustibles going out of the stack, but the difference with these biomass boilers is you actually have embers going out of the furnace with the combustion air. So as soon as you are introduced to more air, you have a source of ignition as well. So that makes it all the more important to address the O2 and not let combustibles escape unnecessarily. I do have a poll here, so I will go ahead and launch that. 1 second. If anybody has any questions, again, feel free to jump in. So this poll, what metrics would you prioritize when assessing the performance of your stoker combustion control system? So this is a rank poll, so you can slide these around. Anyway, thanks, Chris. Go ahead.
Yeah, there was a question about higher O2 at the inlet of precipitators. So an electrostatic precipitator, you're actually charging a voltage between plates, and with high oxygen, if you have too high of oxygen, that can definitely cause your precipitator to wear faster. And also, you definitely need a minimum temperature for those precipitators to do well. If the temperature's too low, it's going to cause maintenance issues. One thing I should mention, actually, let me go back to this diagram. On the ID fan, again, what you're doing here is you're blowing air into the furnace, but your ID fan is usually a much larger fan, and it's pulling harder so that you actually have a slightly negative draft pressure above the grate. You'll have a positive draft pressure below the grate, but negative above. And typically you're running like -1/2 inch of water, so slightly negative. However, as you move down this duct here, you're going to have mechanical separators like cyclones to drop out the big ash, and then you're going to have various bins and other ways of separating ash out. Perhaps there's a baghouse, electrostatic precipitators, maybe the SCRs, SNCRs, I already mentioned that, possibly a scrubber. So there's a lot of things that you're going to have that are after the furnace and before the fan, and at each step the draft pressure in that duct gets lower and lower, so more and more and more of a vacuum. And if they're not tight, you're actually pulling in air at each step there. And so, for a brand new boiler, if you've got 4% coming out the furnace, you're going to have roughly 4% going out the stack after the ID fan. But for something that's been around a while and had ash rubbing on it for decades, you're going to have some leaks, and you're going to be pulling in a little bit of extra oxygen down the road. And so that definitely is relevant to those embers that Chase mentioned that can go down into the back end, as they can sit there and smolder and produce carbon monoxide after they leave the furnace. So having a little bit of excess oxygen can take care of that. Make sure that the embers get burned up before they leave the furnace. Okay, on the O2 trim, so the result of this PID loop on the O2 trim is, there's a lot of ways to do the math here. They used to do it where 50% was kind of in the middle, and below 50 means less air and so forth. What I like to do with modern PIDs that aren't limited to 0 to 100% is actually have 0 be nominal and have it go negative for less air and positive for more air. And then what you can do is say, I want this to go negative 40 to positive 50. And that would allow it to take air out down to 40% less than nominal, or add air up to 50% more than nominal. And that's much more authority for the O2 trim than you typically see in other applications. When you have, let's say you're burning natural gas in a package boiler, you would typically only have plus to minus 10%. If you're doing coal, a lot of times it's plus or minus 20%. And that's because you set those curves and they really stay pretty constant. But because our fuel is so variable, this has to have a lot more automatic authority to keep your O2 where you want it. Some of the O2 trim upsets are predictable, and for any time you have a PID loop where there's a predictable upset, it's advantageous to use feed forward. And that's basically, if something happens like the steam flow changes, then you know that your air demand is about to change, so you may as well go ahead and change your output of the PID loop without waiting for the upset. That's feed forward. So I believe we've now covered the entire diagram. So we've got the air coming from the undergrade air coming from the Boilermaster. That's traditional. Traditionally, the overfire air also comes with Boilermaster, but I'm proposing that for biomass, it's better to run it from percent steam flow. We have an automatically adjusting K here to keep your percent Boilermaster and your percent steam flow aligned over the long term. They will swing against each other in the short term as the furnace cycles, but over the long term, they need to stay aligned. These curves for O2 trim set point and your air curves, that's traditional in pretty much any boiler that has these flows will have those curves, so there's nothing new there. And then the operators need to be able to bias between overfire and undergrade depending on their observations of the characterization of the fuel. And the end goal is to spread that fireball up into the furnace so that your peak temperature is less and you have more surface area being actually used to transfer heat into your water in the tubes, but not so much that you do want to contain the combustion inside the furnace.
Chris, on this diagram, and when you go into these plants that have biomass boilers, where are you seeing people struggling the most? Like, what do you have to go in here and adjust most frequently?
Well, the main thing is, as far as tuning.
Yeah.
Oh yeah, the trickiest one to tune for sure is the steam. This PID loop for the Plant Master, because it's so variable. And actually, we're going to talk about that here in a second. But that steam Plant Master. The trick is you've committed the fuel to the grate. And so if it takes off, you have to burn it, but that's going to make your steam jump up. The other one that's traditionally been tricky is there's a whole There's a whole aspect of biofuel that I'm not even touching here, which is the delivery. Like basically you either got, it's typically trucks bringing in chipped wood, but you may have trucks bringing in, you know, tree trunks or whatever. You may have rail cars or whatever, bringing in that wood. And then it's got to be stored. It's got to be run up a bunch of conveyors. A lot of times they chip it on site. There's hoppers, and then there's, you know, belts to move from the hoppers into the stokers and all that stuff. And there's just a lot of opportunity to have an interruption in fuel flow. And so what'll happen? Oh yeah, exactly. Magnets to pull out nails and stuff out of your wood, so you're not tearing up your stokers and tearing up your grates and all that. So there's a lot of opportunity for something to trip that interrupts the flow of fuel to the stoker. And then what'll happen is your if that happens, your steam flow will stump. There's also typically there's going to be a control loop that's not part of the combustion control, but just to make sure that you're delivering the right amount of fuel to the stokers so that their day bins stay partially full but don't overflow. That's, you know, we're not really even talking about that, but that's a tricky loop. But yeah, as far as what's on here, definitely the plant master is the trickiest to tune. The airflows, those are easy. You know, you're just adjusting a damper to hit a desired flow, piece of cake. Oxygen, that's a little tricky, but it's usually pretty straightforward to tune your oxygen loop. So yeah, of the 4 loops here, yeah, definitely plant master.
Okay, great. And my fault for slowing you down, but we have about 13 minutes left. I think you got about 10 slides left, just so you know.
Yeah. So, and really, this is the kind of the core. We're wrapping up here, but I've got some hints on exactly the tuning issues that we were just talking about. So let's go through those. Certainly, if there's a question about this diagram, that would be good to see those. But okay, so I'm going to move on here. Having Sorry, having computer issue here. Let me launch the slideshow again.
I could share it too, Chris, if you can't get it going.
Okay, let me.
Tell you what, while you're dealing with that, I'll go ahead and launch our last poll a little early.
Okay.
There you go. Are you looking for support for any biomass combustion control systems? Pretty straightforward. There you go. Get back on slide 19 or so.
Yeah, I'm going to need you to do this. I don't know what's going on. Sorry, Chief.
Yeah, no problem. Sorry, everyone. Right. Back where we were. 1 second. Slide 21. No, 20. There we go. All right, Chris, can you see that?
Yeah. Okay, go ahead and go to the next one.
Okay.
I guess it's the slideshow itself, huh?
Is it not showing? I'm showing your chart and talking about set point ramping and outrun prevention.
Okay, yeah, it just came up. All right, so okay, yeah, so feed forward. This is a fairly typical thing that we want to do. If you know what things are going to use steam for your this again, this gets to that tricky to tune plant master loop. If you know other users of steam, such as soot blowers or the actual process load for the steam, if it's not just a turbine, then you can certainly use that feed forward to the plant master. We were talking about fuel interruptions. This is a real chart from a real biomass facility that underwent a fuel interruption, and I had put in what I call outrun prevention. So what you see is the red is the header steam pressure, and the green is the set point, and the set point should ramp. And so what happens is the steam started slumping because we actually had an interruption in our biofuel. And so I had programmed it to have the ramping set point for the plant master never be more than 40 psi above the actual. And so you can see that green followed the actual down from the interruption all the way until 1050. And you can see we suddenly got fuel back at 1050. And what this does is make it so that your plant master doesn't run all the way to 100% and demand maximum fuel when there is no fuel, which that windup would cause a huge overshoot. And so this mitigated that. And what happened was is we ramped back up to our nominal pressure in control. And then when we got back to our nominal pressure, you can see there was basically no overshoot. We went right back into good control pretty much as soon as we got there. So that outrun prevention where you just use your ramping set point and make sure you never get more than 40 psi or whatever. If this is a fairly high pressure boiler, 1950 psi. If it was a 120 pound boiler, you know, I'd probably have 10 psi instead of 40. So that helps. The other thing I want to point out about this slide is if you look at the very end of the ramp as it comes back up, there is a curve on the green. So you see a sharp elbow when it goes down and a nice little curve. And I call that a terminal deceleration. And that terminal deceleration also helps with overshoot because what you're doing is you're saying, okay, you need to back off on the fuel because we're about to get to set point instead of just going all the way to set point and then backing off, at which point you're going to overshoot a little bit. So next slide. Yeah, there's that terminal deceleration. Oh, the other thing is, sorry, go back to the previous slide. What you'll notice on that set point, the green, when we're coming back up, you'll notice that that green actually accelerates. And the reason it accelerates is I have the ramp rate is a variable on the, and this is a pressure ramp rate. And the pressure ramp rate is tied to a steam table that looks up the temperature. And what we're doing is we're ramping at a rate that causes the temperature to rise at 100 degrees per hour, which is typically the maximum rate that you want to come up to protect your refractory. And so variable ramp rate on the pressure matching a steam, a temperature constant ramp is appropriate. Okay, 2 slides. Raise inhibits, yeah, very important. So what you have here is there's a bunch of things which it's like your boiler is okay right now, but if you went up anymore, you're going to cause a trip. And so for those, you want to use a raise inhibit. So if you're, let's say your boiler feed water valve is 90% open, then you're done. You know, you can be here, but you don't want to go up anymore. You're going to trip out on low drum level, raise inhibit. If your air is low, you want to not add any more fuel. If your oxygen is low, you want to not add any fuel. And what will happen is that raise inhibit applies to the boiler master. And then once it releases, then you can go up. So as your air cycles, you just want to make sure you're not going up on fuel when you're already behind on air. And you definitely don't want to go up if your drum is, if you're out of boiler feed water. There may be temperatures, which like stack temperatures that may cause a trip. And once those get close to their limit, you don't want to necessarily run back, but you don't want to go higher either. So that's a raise inhibit. Next one.
Hey, Chris, did we, there was a question in the chat. I don't know if we addressed it. Is there typically a difference in how it is ran up to get up to heat versus keeping it steady in the control loop?
Oh, yeah. So sometimes people will do dynamic tuning where you have different tuning settings. I typically don't do that, and because what I like to do is always be in control. So you never let your controller go to 100%. And like if your ramp rate is so fast that you're asking for 100% fuel, you're ramping too fast to be in control, and you're almost guaranteed to overshoot when you get there. In that case, you could, if you're just really in a hurry, I guess you could use a higher proportional action and mitigate that. But I would rather just slow the ramp down, take your time, be in control the whole time. And if you do that, then you can use the same tuning settings for the ramp and the steady state. Is that, yeah, let me know if that doesn't answer the question. There are other applications for heating where some ovens, it makes sense to just get up to temperature as fast as possible. And I definitely use a different algorithm there. Typically, I actually run 100% up until you get within a few degrees of set point and then release the auto. But that's, I would not do that with a boiler.
Okay.
We're running out of time. Basically, cross limiting, you can't really cross limit properly with solid fuel, so don't. Use raise inhibits instead. So yeah, let's move on. Yeah, same thing there. Move on. I don't think we really have time to get into limited windup. That's a somewhat complex topic, so let's skip that.
I'm on auto manual dependencies. Are you seeing that?
Okay, there it goes. Yeah, so basically the idea here, and this is a general thing that applies to all boilers, is if you have a cascade and the slave is not in cascade, then you want to make sure that the master output tracks the slave set point. And this is just generally applicable. Like if your boiler master, if your fuel screws are in manual, then your fuel master and your boiler master should track the screw speed so that when you put it in auto, there is bumpless transfer. It just picks up where you left off. Okay.
Bumpless transfer.
Yeah, that's the same thing we just talked about. This is kind of more details, and you can look at the details later. But the idea is here's a list of situations where you might have cascade, where the slave may be in manual. Yeah, you want to run back. I mentioned raise inhibits before. There are some situations where you actually really do need to run back. Sometimes there's like an area, and this really needs a proper HAZOP review, but there may be situations where you don't actually have to trip the boiler, but there's a situation bad enough where you definitely need to reduce loads to no more than 40%. And so like if your overfire air fan tripped, for example, for some boilers, you just need to trip the whole boiler. For other boilers, it may make sense to run your load down to 30 or 40% while you get that fan restarted, but you don't necessarily have to trip the boiler. So that would be a run back example. You may also want to run back where if your O2 goes low, maybe for the first minute, you just run back your fuel rate. And then if you can avoid a trip by doing that, then that's good. Again, this requires a proper HAZOP review. So whether you even want to do that. This is, oh yeah, so for stokers, VFDs, typically you don't want to run a VFD lower than 15 hertz, which is 25% speed. If you want to run, let's say 5%. If you want to run 5% load, but your screws won't run less than 25%, you don't want to stop some screws and run others. You want even distribution over your grate, so you want to run all the screws. But what you can do is run all the screws for say 12 seconds out of every minute or 6 seconds out of every 30 seconds. at their minimum 25% speed, and that will give you overall an average of 5% load. And that's an effective way to run at very low loads, which you wouldn't want to do that continuously, but that is very helpful on startup when you're first coming up. Yeah, so 3-element drum control, typically you do either 1 or 3. 1 would be you're only looking at drum level. 3 is you're looking at drum level, which sets a boiler feed water flow rate. And then you use your steam flow rate as feed forward. The point I'm making here is you can also do 2-element, which is you ignore the steam flow when it's very low, because it's typically extremely noisy when you get below about 20% steam flow. But you can still do the cascade from the drum level to the boiler feed water flow controller. So that would be kind of like 2-element drum control, and that works well in a lot of situations. Yeah, so modern controllers, you should have steam table curves in your controller. So anytime you have a saturated steam pressure, like your drum pressure and your header pressure, well, definitely your drum pressure and your header if you don't have a superheater, you should be able to just calculate the temperature at that point and display that for the operator as well. And that's often useful information. Same is true for like soot blower pressures, as that's typically saturated.
Yeah, we this came up in our Zwali project, right? We were measuring steam flow across the control valves, and we needed the properties of the steam. So we took the upstream pressure measurement. It was saturated steam, so we took the upstream pressure measurement, and we were able to get all of our densities and everything else we were using from that, and then calculate the flow across the valve. So
Yeah. Yep. Yeah, so yeah, these advanced controllers have a lot of capabilities, and let's use them. So.
And that is it. I don't see any more questions, although we will hang out for a minute if anybody has any questions. We really appreciate everybody joining. Apologize for going over a little bit, but that's usually a good sign that we had some good interaction. So I think this was a good presentation. It will be available. The recording will be available on our website in the webinar section if you'd like to share with any of your colleagues. I'd like to thank Chris Hardy and Cross Company again for participating. It's we're honored to have experts like Chris join our showcase webinar series, and I think this was really interesting. And again, we appreciate everybody attending. Also, you can request a PDH certificate. Just email me there, cbean@steammanagement.com, and we'll get that back to you shortly. Chris, any other comments about the presentation?
I don't think so. I just appreciate everybody joining, and thanks for the questions, and definitely reach out to me if there's further questions.
Okay.
Or Chase.
Yeah, definitely. And again, we'll hang out for a few minutes in case anybody has any questions. We have a question. Is it possible to get a copy of the slide deck? Yes, we're happy to share that. Just kind of do the same as the PDH certificate. Just reach out to me, and I'll email that back to you if you want that.
Yeah, there's a question about steam tables. Typically, the modern controller doesn't necessarily have like a built-in steam table, but there's almost always a function block that you can add. For example, I do a lot of my work in Allen Bradley with the plant PAX library, and the plant PAX library has steam tables where you look up pressure from really all the properties from temperature, or all the properties from saturated pressure, or you can feed it temperature and pressure, and it will tell you what regime you're in, whether you're superheated, saturated, or liquid, and give you all the properties. And then most modern controllers have something equivalent to that, where there's some library you can pull in, or worst case scenario, you can just look up the steam table. They have like 5 regimes with various polynomials, and you just pick the ones you need and do the calculation in the controller. They've all got plenty of memory and horsepower.
Yeah, good question. All right, we're at 12:06. No more questions. I think it's safe to close it out at this point. But again, feel free to reach out to me if you want the slide deck or Chris's contact information. Happy to share that PDA certificate as well. And be sure to look at that case study. That was a great project that we partnered with Cross Company on. That was in the chat, or I can send you a PDF version of that if you like. And again, the webinar will be available on our website. So please share that with anybody you think might be interested. And we appreciate everybody joining, and we're going to close it out. Thank you.
Thanks.